Hello class, this is section 13.2, the chi-square test for association independence. And we're going to go over this last chi-square test, even though it won't actually be covered on the AP test, but I'm going to go over it anyway just to complete the chapter. So our goals are to perform the chi-square test for association independence. And we're going to show how a two-sample z-test for proportions is related to a test for homogeneity. And then you'll have to choose which chi-square test is appropriate given the data. All right, in the last section, we looked at two-way tables from independent groups of observations from different populations. We compared the distribution of the categorical variables in several populations or treatments, and to do that, you use the chi-square test for homogeneity. So, for example, if you were to sample freshmen and sophomores, and then to see if there was a difference between the two distributions, that's a chi-square test for homogeneity. Now, you can also use a two-way table with a single population classified according to two categorical variables. Here we want to analyze the relationship between the variables. So here we're looking at a single population, and we're going to see if there's an association or relationship between the two categorical variables. So here's our example. It's about anger and heart disease, nothing more pleasant than anger and heart disease. You can read the specs yourself, and if you need to pause the video, you can. I'm going to move on. Here's the two-way table that summarizes the data. So you have those with coronary heart disease and those without coronary heart disease, and you have three different anger levels: low anger, moderate anger, and high anger. To calculate the conditional distributions, we need to look at the relationship between anger level and coronary heart disease status, CHD. So we're going to divide it up by anger. So we have low anger, those with moderate anger, and those with high anger. Among those with low anger, 53 out of 3110 got coronary heart disease for about 0.017. Those without coronary heart disease out of the low anger group is about 0.983. And you can do the same calculations for moderate and high anger. Notice here we are dividing by the total people in each group, in each anger group. Now, keep in mind this was one sample. This wasn't three separate samples where you looked at people with low anger, then a separate group with moderate, and then a separate group with high. This was all one group, and then subsequently classified by their anger levels and examine whether or not they got coronary heart disease. So here's a bar graph comparing the conditional distributions, looking at the percentage of those that actually got coronary heart disease. You can quickly see that those with higher anger tended to have a higher incidence of heart disease. That's not that surprising. So there are two categorical variables here. First, you have the test score, whether it's low anger, moderate anger, or high anger. And then the second variable is heart disease, whether or not they had heart disease or whether they didn't. And the question we want to answer is, do these data provide convincing evidence of an association between the variables in the larger population? Or could this have just arisen from random sampling? So notice here we are looking at one population. We want to see if there's an association or a relationship between anger levels and heart disease. This is different than homogeneity. If we took a homogeneity test, we might have three different populations, different anger levels, and want to see if there's a difference in the percentage of those that got heart disease. So it seems very semantics, but it's actually a very important distinction between how the data are collected for these two different tests. So the chi-square test for association or independence, you can call it either way, and we have the same three conditions: random, large sample, and independent. The null is that there is no association between two categorical variables in the population of interest, and the alternative is that there is an association between two categorical variables in the population of interest. Notice one population, and we want to see if there's an association, a relationship between the two categorical variables. Now that's one way to frame it using the test for association. Instead of framing it as an association test, you can frame it as an independence test. The null hypothesis is that the two categorical variables are independent in the population of interest. Again, one population. The alternative is that the two categorical variables are not independent in the population of interest. In other words, there's a relationship. Knowing something about one variable tells you information about the likelihood of something with the other variable happening. Now, the way you do the calculations is very similar. You're going to find the expected counts. You calculate them the exact same way you did it with the homogeneity test, which is basically the row total times the column total divided by the table total. And you're going to find the difference between the observed and expected, square it, divided by the expected, and add it up for all the cells. And just like for the chi-square test for homogeneity, the degrees of freedom is calculated by taking the number of rows minus 1 times the number of columns minus 1. The conditions are that the data come from a single random sample or random experiment. Usually it's going to be a single random sample where you classify people based on how they respond. The large sample size condition is the same. All expected counts are at least 5. And independent observations. Now, if you're going to sample, again, you need to make sure that the population is at least 10 times the size of the sample. So here are the observed counts. Now to find the expected counts, again, you are going to take the row total times the column total divided by the table total. And you would do it the same way in your calculator using the chi-square test. So here are the expected counts. You can see, again, decimal points are totally fine. If you add up the expected counts for each row and each column, they're going to equal the total for each row and column. So let's go through the 4 steps. First, we want to state the procedure, who the population is, and the hypotheses. The null is that there is no association between anger and heart disease in the population of people with normal blood pressure. The alternative is that there is an association between anger and heart disease in the population of those with normal blood pressure. This is the chi-square test for association. And there's an alpha of 0.05 just like before. So you can frame it as independent or association. Either way is fine. We're going to go through the conditions. We are told that the data come from a random sample of 8,474 individuals with normal blood pressure. On the previous chart, you saw all 6 expected counts are well above 5. And the population of people with normal blood pressure is probably over 84,740, because even in a place like America where people are obese and not very healthy, there's still a lot of people with normal blood pressure. All right, so doing the calculations, our DF is the row total minus 1 times the column total minus 1. So 2 rows, 3 columns, DF is equal to 2 times 1 or 2. To find the chi-square, you're going to take each observed value, subtract the expected, square it, divided by the expected, add them all up. And you get a chi-square of 16.077 with a p-value of 0.00032. Now you would do this on your calculator the exact same way you did it with the chi-square test for homogeneity. You'd use matrices, put the observed count into matrix A, run the test, it'll output the expected counts into matrix B. And there's the result from the calculator. So you notice that the p-value was very, very low, very, very much below 0.05, so we reject the null hypothesis in favor of the alternative. There's pretty convincing evidence that there is an association between anger level and heart disease in the population of those with normal blood pressure. So again, you wanted to see if there's a relationship, a connection, association between the 2 categorical variables within a single population. All right, so the question might come up, do we use the z-test for proportions or do we use the chi-square test for homogeneity? So we're going to kind of double back to homogeneity here. We can use the chi-square test for homogeneity to compare any number of proportions. The results from the chi-square test for 2 proportions, though, is the same as a 2-sided z-test for 2 proportions. But you'd rather use a z-test instead of a chi-square because it gives you the possibility of a 1-sided test. You want to see one proportion is higher than the other, whereas chi-square only tells you if there's a difference. And you can actually calculate a confidence interval for the difference in their proportions, which you can't do on chi-square. Chi-square basically tells you, is there an association or is there a difference or is there not a difference? We've learned 3 chi-square procedures. How do you know which one to use? So chi-square goodness of fit is the easiest because it's the only one with only one categorical variable. So if you remember the M&Ms, the only categorical variable is color. So chi-square goodness of fit will have one sample and only one variable with more than one categorical value. So one sample, one variable is chi-square goodness of fit. Now the difference between the homogeneity and the association test is a little trickier. A test for homogeneity asks questions about the differences between populations. So notice plural, populations, different groups. Is there a difference? Whereas for association, it asks about how a single variable, how a single population is distributed. Is there an association within that population? So instead of focusing on those things, what you really want to focus on is how the data were produced. If you have 2 or more independent random samples or randomized treatments, then that's the chi-square test for homogeneity. You want to see if there's a difference between the samples, the populations, or the experimental groups. If there's a single random sample where you basically put everyone into, take everyone from one pool and then separate them by category, that's a test for association. Is there a relationship within the population between 2 categorical variables? So here's our second to last example. I'll probably go through the last example as an extra, but you probably don't need to go through it. 2 independent random samples of adults were asked, do you favor or oppose the death penalty? So you can basically go ahead and read it. You have education levels, and you basically want to see, is there a difference between the proportion of those that support the death penalty based on their highest education level attained. So here are the data. We're going to do a two-sample z-test like we did in chapter 12 to see if there's a difference in the two proportions who favor the death penalty, and then we're going to do a chi-square test for homogeneity to see if there's a difference. So step 1, P1 is the actual proportion of those with a high school degree who favor the death penalty, and P2 is those with a bachelor's degree who favor the death penalty. The two-sample z-test, and the null hypothesis is that P1 equals P2. The alternative is P1 not equals to P2. We want to see if there's a difference between the education level and whether or not there's a difference in the proportion of those who favor the death penalty. So the conditions are basically the same as we looked at chapter 12. You have two random samples. Again, for a two-sample z-test for proportions, you need N1 P1 hat, N1 1 minus P1 hat, N2 P2 hat, N2 1 minus P2 hat. All of those are at least 10. And finally, we know there are more than 13,800 and 5,040 high school and college grads in the population, respectively. So to calculate the z-statistic, you need to find each sample proportion. Don't forget for the two-sample z-test, you need to pool the proportions together. So that's what P hat C is. And the z-statistic is P1 hat minus P2 hat over the square root of P hat C times 1 minus P hat C times the quantity 1 over N1 plus 1 over N2. So we put all those numbers in the formula. You end up with a z-statistic of 4.19 with a p-value of 2.74 times 10 to the negative fifth. So the p-value is very, very low. There's a very strong convincing evidence of a difference in the proportions of high school and college grads that support the death penalty. We reject the null hypothesis. So that's doing it using a two-sample z-test. Now we're going to look at it with chi-square. Here are the observed and expected counts. Notice that I've separated into a two-way table. We have education level, high school, bachelor's, and we have favor or oppose. And we find the expected counts for each cell by taking the row total times the column total divided by the table total. So we want to test the null hypothesis that there is no difference in the proportion for those who support the death penalty based on education level. Alternatively, there is a difference in the proportion for those who support the death penalty among people with different education levels. This is a chi-square test for homogeneity. Two different groups. One group has high school degrees, one group has college degrees, two samples, test for homogeneity. We want to see if there's a difference. Conditions, random. We basically went through it with the z-test. So they're both random samples. Large sample size, if you look at the previous slide, all four expected counts are at least 5. And independent, same as above. We know that there are more than however many thousand people with a high school degree, 13,800 high school grads, and 5,040 college grads in the population. So the calculation for chi-square, the DF is 1. 1 times 1 is 1. Chi-square is observed minus expected square divided by expected for all four blocks. Notice I only put in the first and the last one. You end up with a chi-square value of 17.59 and a p-value of 2.74 times 10 to the negative fifth. Notice that the p-value is exactly the same as it was when we did the two-sample z-test. So we're going to have the same conclusion. There's very strong evidence of a difference between the proportions of high school and college grads that support the death penalty. We still reject the null. So notice that the interpretation and the conclusion is the same. Now, one last thing I want you to notice is whether you use the two proportion z-test or the chi-square test for homogeneity, that the p-values are almost exactly the same. 2.74 times 10 to the negative fifth for the two prop test. 2.74 times 10 to the negative fifth for the chi-square test. I also want you to notice that if you take the z-statistic in the two prop z-test and square it, you get 17.59. And if you look at the chi-square, you get exactly 17.59. They are exactly the same. So if you take the z-statistic and square it, it equals the chi-square value. Isn't that nuts? Cool. That's it for sections 13.2 and the chi-square test for association independence. If you have any questions, you are welcome to ask me using email or during one of our chats.